So the final type of boundary that we have is what we call a transform boundary. And transform boundaries are places where the crust is, or the two plates are sliding past one another. So we talked about divergent boundaries where they're moving apart from one another, and convergent boundaries where they're coming together. And now we're talking about transform boundaries. And these boundaries have one plate going in one direction, another plate going in the other direction. And the stress ends up building up between the plates, and eventually it's enough to cause that to slip quickly, and then you get an earthquake. So these are where you get major faults happening, major earthquakes happening. You also do get movement to cause earthquakes in convergent boundaries, but I can talk to you more about that, but here we get a lot of earthquakes along these transform boundaries, and the San Andreas Fault is a really good example of that. And here's North America. This is just a screenshot of the reference table, and sorry that's a little bit fuzzy, but you can see from the key at the bottom of the reference table the transform boundaries look like this. And here is California, and if you look, one side of California is on, one part of California is on the Pacific plate, and one part is on the North American plate, and the North American plate at this point is moving south. Here on the other side is moving north. And so yes, there is a place where San Diego is on one side, and San Francisco is on the other, and eventually they'll be moving sort of away from one another. And people always say, oh well, California is going to split off and fall into the ocean. That's not going to happen. What'll end up happening is these will just get further and further apart. So these cities will get further and further apart, but it's going to take millions of years. I mean, these plates move at the speed of the way that your fingernails grow, a few inches a year. So they move very, very slowly. So it takes millions of years for these continents to separate and move, and that was one of the problems with the idea of plate tectonics, is that the idea that it would take millions and millions and millions of years, hundreds of millions of years, to have the continents moved so much that they could be that far apart from one another. So these transform boundaries where you have one plate moving past another. There's some things that help us show that other evidence that plates have moved. One of these is the benchmarks, and we've seen these benchmarks in topographic maps. There are places that are labeled with the exact elevation, and scientists can determine how much that's changed. So they go back in 10 years or 20 years or 30 years and see how much that's changed. Or in the Himalayas, they actually have sensors that send information via satellite, so they can look at how much it changes in real time. So when an earthquake happens, they can see if the Himalayas have been raised up at all. Another piece of evidence is that fish and marine fossils, marine meaning ocean, fossils, can be found at the mountaintops. There's places on the Himalayas where you can find shark teeth fossils, and it's not that somebody carried these fossils up there and dropped them. They're found in the rock, and so that means that either the whole world was covered 6 miles with water, or the rocks have gone up from there. And we know that the ocean levels haven't changed that much, because the water would have had to go someplace, and we can account for all the water on the earth. So we know that the mountains that rock had to come from a place that was underwater at some time. There are also places where you have shallow fish that live in shallow water, buried deep in the ocean floor. So those areas have sunk. So where you have two plates that are coming together, and one is subducting under the other, the ocean, it gets deeper there, and so those shallow marine fossils can be found in areas where the water is very deep. And then we can also start looking at the rock itself. And this is just normal undisturbed rock. Rock layers usually are laid down horizontally, where you have one layer, like cake layers, one on top of the other. They can be tilted, which must have been formed when some big movement had to happen to tilt those layers up, because rock layers are not laid down at an angle. And then we also see where there's rocks are folded, where they're actually bent. And then here we talked about this with earthquakes, but when two rocks break, the rock layers can shift, and that break happens right along here, and you get the shift in these rocks causing this faulting to happen. So we can get any of these. We go out and look at rock layers, you can see these things, and there are some places around here you can see tilted rocks or faulted rocks. The last piece of evidence that we'll talk more about in class, and we'll do a lab on this, is something called a hot spot. And this is a place where molten rock is breaking up through the crust in the middle of a plate. So this is happening if this is the ocean crust and here's the surface of the water. There's what's called a magma plume underneath the lithosphere, and if this is the lithospheric crust, the lithosphere in the upper part of the mantle, that tectonic plate, this molten rock breaks through here and starts to seep out onto the ocean floor, and it forms a little volcano that builds up over time, and as time goes by, eventually enough lava flows out of there that a little island is built, and that's where the Hawaiian Islands came from. So we'll talk more about how that's significant and how we get these chains of islands there, but I just want you to be familiar with that term of a hotspot. So that's the end of notes for this unit, and if you have any questions, as always, feel free to ask. I'm more than happy to help you out. So I hope you had a great day. Take care.